Hey, we are in chapter 8 finally, and we're going to talk about something called the geometric mean. Not that big of a deal. It's just a concept that is going to be explained as if you're looking for the geometric mean of two numbers, let's say some number A and B. So the geometric mean of A and B would be simply, drum roll please, the square root of the product of A and B. So that's legitimately what the definition of the geometric mean is. Now let's see where it came from. So the idea of geometric mean comes from, it basically means a proportion that has the same number that are at the means, right? So remember when we had proportions, we had the product of the means is equal to the product of the extremes. So if you had a portion where A is to X and then X is to B, then the geometric mean, right? If we remember the proportion situation that we talked about, we would multiply A times B, multiply X times X, so we get AB is equal to X squared. Let me make this point a little bit finer. So if the product of AB is equal to X squared, if I have to solve for X, I'm going to take the square root of both sides. And then so when I do that, X is equal to the square root of AB. I won't do, if I were teaching an algebra class, I would totally tell you that X is equal to plus or minus AB, but since we are dealing with geometry and real lengths, we're not going to have a negative length, so the geometric mean is going to be positive. So in a key concept nutshell way, the text writes it out like this. The geometric mean between two positive numbers A and B is a number X such that they have this relationship, X squared is equal to AB, or X is equal to the square root of AB. Specific example would be that the geometric mean of 9 and 6 is, 9 and 4 is 6 because 9 times 4 is 36. Square root of 36 is 6. Cool? All right, so that's the geometric mean. So here we can apply our knowledge of the geometric mean. One way we can do it is to set it up as 8 over X is equal to X over 10 and solve that. Or we could simply say that X is equal to the square root of 8 times 10, because that's ultimately where we're going. So let's talk about how we would do this. Obviously, if we cross multiplied here, we'd eventually get here. So I'm just going to start with X is equal to the square root of 8 times 10. So X is equal to the square root of 80. And yes, we could pull out a calculator and get that it's going to be a number that's pretty close to 9, but not quite 9. But when we simplify square roots, what we do is we look for perfect squares that divide evenly into the number that's underneath the radical. And so if you remember, in the back of your mind, you're thinking about all the perfect squares you memorized in your life because you're that type of kid. So 1 is a perfect square because 1 times 1 is 1. And 4 is a perfect square because 2 times 2 is 4. You see where we're going. 9, 3 times 3. 16, 4 times 4. 25. You memorize these, so you're like totally saying them with me. You're like, write faster because they're spewing out of our craniums so quickly. We just need you to hurry up and get the answer. All right, so as you see, I go all the way down till I get past the number. And so so I'm past 81, and I'm past 80 with 81, so I don't need to go any further with my memory. What I'm doing is looking for the greatest perfect square that divides evenly into 80. And that takes a little bit of practice. 1 does. That's no fun because that's just 1 times 80, and that just gets us back to the same place. 4 is pretty good. I'm going to keep going, see if there's another one. 16, right? 16 times 5. So I rewrite this as 16 times 5. And now to simplify this, I say, okay, which one can I take the square root of? 16. I engineered that. So the square root of 16 is 4. And the square root of 5 can't be done. So the way I would write the square root of 80 in a simplified form would be X is equal to 4 root 5. You should have seen this before. If you haven't, I talk a lot about math all the time. I feel like I may have explained this before, but if you didn't get it then, if you don't understand it, let me know. I will happily go through a little mini lesson on simplifying radicals. All right, Now, so that's our answer. Dun, 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 dun. Let's go ahead and look at some more cool information. So if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. That's kind of fly. So here's this right triangle, ABC, where the right angle is at C, and then an altitude. Remember what an altitude is. It's like dropping a perpendicular from a particular vertex to the other side. And so when you drop a perpendicular, you get a perpendicular angle. So when you do that, you instantly create two additional triangles, this little one, and this other not so little one, that is similar to the other triangle. Kinda cool. And that's not a hard thing to prove when you recognize, okay, so all three of these triangles, the big one and these two little ones have right angles. And then like if we look at this big one and medium one, they both share angle A. Therefore, their third angle must be equivalent, right? So if they have 90 degrees in common, they both share angle A, then angle B and this little angle C here, not that C, but this C here have to be equivalent. And we can make a similar argument here with angle B being shared with the big triangle and this little teensy weensy triangle, both of them being right angle triangles, and then this angle C is equal to this angle A. Think about it. It's kind of mesmerizing and fly all at once. Okay, so with that in mind, with this theorem taken care of, we're going to move on to taking a look at a problem that deals with this concept. So what I'm basically going to do here is just take a moment to observe. I took some time to erase the explanation that the text was giving, because sometimes I don't find it helpful to read an explanation as opposed to explain. So it wasn't like cheating, but I just want to let you know what happened there if you're like, there was information that's gone. All right, so now we're looking at this triangle, this triangle that has the altitude situation. So we know that there are three similar triangles here. Let's see if we can write them down. So write a similarity statement identifying the three similar triangles. All right, good. So let's start off with just naming one triangle. And it might be kind of cool to start at the right angle, just so we can have a little bit of consistency. So I'm going to start with G, looking at the big triangle. I'm going to start with GFH. All right. So I've named the first one, GFH. And you remember when we name similar triangles, we need to maintain the order of equality for the angles. You with me? So that's going to be important. So this next triangle, let's try to be all color coordinated, and let's do a little blue triangle. Okay. So if we do this little triangle here, we're going to start with the right angle, and the right angle would be J. Does that make sense? Because G is the right angle then of the large triangle, J, and then we're going to start with the right angle of this one. Now this one's a little bit tricky. Not tricky, but tricky. This one's a little tricky because you got to think, okay, what angle corresponds with angle F of the big triangle and the little triangle? And if you notice, the angle that corresponds with angle F is angle F because they share it. So I'm going to put F right here. And now we know that H would have to be the same measure as this little tiny sliver of angle G, because, you know, if two angles of a triangle are congruent with two angles of another triangle, the third one is automatically congruent. So that's not too bad what we just did there. Let's do this next one. We're going to do the medium triangle, which I'm going to color in red there, and let's go ahead and name this triangle. So we'll start off with the right angle. The right angle of this triangle is J, but we're talking about this other side, that's okay. And then now we need to figure out what angle is equivalent to F from the other ones, because notice F isn't a part of that. So sometimes that's hard, right? Because it's like, well, which one? So what's easier is to say, okay, well, what angle is equivalent to H, right? Because that has to be the third letter that you write, and the angle equivalent to H is H, and therefore the angle that must be equivalent to F from the original, from F from the original larger triangle has to be this sliver of G. So there's our equivalency statement or our similarity statement for that problem. So let's get into some other cool theorems that we have. Do you say cool theorems at home? Mom, I learned some cool theorems. Probably not, but these are cool. All right, so we're going to talk about the geometric mean and the altitude and how they're related. And as you can see from this picture, so we talked about the geometric mean earlier, and you're like, okay, whatever. But why do we know this? Why do we care about it? Because of this really cool result. Because this altitude splits this right triangle into all of these little similar triangles, there's a relationship that has evolved or that has come up through that relationship to these similar triangles, and it's that the altitude intersects this hypotenuse that's alongside of the larger triangle or of any right triangle across from its right angle. It bisects or not bisects, it cuts it into two parts such that that is the geometric mean. So I'm saying a lot of things. Let's look at the picture. X and H, X and Y and H have this relationship. Therefore, H, this altitude, is the geometric mean of X and Y. So you can find a lot of information from this. And of course, we will give you the opportunity to do so soon. So let's look at this next one, the geometric mean in terms of the legs. So now this one's a little bit, for me, this one's a little bit harder to hold on to than this one. This one kind of feels nice and symmetric. Hey, I'm the geometric mean of you two. But this one over here, not so much. So let's pay attention. So B is the geometric mean of C and X. So again, we're dealing with this altitude and what's broken down. So I'm going to use my highlighters because that's always fun. B, let me make it a little bit smaller. B, this side here, is the geometric mean of this little bit and this big bit here. It's the geometric mean of B, of C and X. All right? And then similarly, A is the geometric mean of, sorry, I don't think when I copied this over, I got all the deets right. This is Y. So, and A is the geometric mean of X and of Y and C. Kind of cool, right? So you got this whole situation where the geometric mean can give you some information about the sides of these triangles when you have them kind of nested together. So I'm going to do something that I used to do when I was in geometry myself. I would literally draw this picture to help me remember that this dark green line is the geometric mean of these two light green lines. Like I would highlight it with like colored pencils or something. And then I would do this, like stay with me because this is basically just an encapsulation of what we just talked about. And this dark orange line is the geometric mean of this part and this part. Like, so if I had a test, I would write this on the test to remember. And then this dark blue line is the geometric mean of this segment and then this whole thing here. So this is like my mental picture of how everything relates to one another in this whole geometric mean business. Like I said, the green one is easy for me to remember, like just to go, yeah, that kind of makes sense. This is the geometric mean of these two things. But the blue one and the orange one is a little bit harder. So maybe this might be helpful as we move forward. Okay, with that in mind, let's apply it to this problem so we can figure out what X, Y, and Z are. So if you notice, X is the altitude, so it's the geometric mean of these two parts, 20 and 5. So I would write X is equal to the square root of 20 times 5, which we know is X is equal to the square root of 100. X equals 10. Let's do the next one. So Y, as I've indicated here in blue, is going to be the geometric mean of 5 and 25. 5 and 25, because 5 plus 20 is 25. And so here's the work for that. And then Z similarly will be the geometric mean, kind of like this orange, of this little piece and the whole piece. So 20 and 20 plus 5, 25. And so we did that here with 20 times 25, giving me 500. factoring it out so I get the greatest square root, and I simplify it here. I'll talk to you guys soon.